Welcome back. This video will serve as a brief look at temperature scales and also the meaning of temperature. So let's consider a pot of water over the flame of a stovetop. Imagine leaving the flame on underneath that pot of water for 1 minute. The temperature of the water should increase. So let's suppose that it's not boiling yet, because you probably know that once water reaches the boiling temperature, it stays at that temperature until all the water has been boiled. We're talking about a phase change there. I'll have a separate video looking at phase changes. So if you leave it on for 1 minute, there's a certain temperature increase, which I'll call delta T1. This is supposed to say for 2 minutes feeding. Let me pause and fix that. Okay. If instead of 1 minute, you had left the flame on for 2 minutes, you would expect there to be a larger increase in temperature. In fact, the reasonable expectation would be that the temperature increase is double what it was previously. So twice as long, you would expect twice the increase in temperature. Now, you could measure that temperature on a variety of scales. You've probably heard of the Fahrenheit scale, the Celsius scale, and the Kelvin scale, all of which we'll be using in the next 2 chapters. So 1 minute versus 2 minutes, the increase in temperature on the Fahrenheit scale for 2 minutes would be double what the increase in temperature would be on the Fahrenheit scale for 1 minute. But the same statement would hold for the Celsius scale as well. Measure the temperature before and after 1 minute of flame, and then do the same thing for 2 minutes of flame. The increase in temperature for 2 minutes of flame should be double what the increase in temperature would be for 1 minute of flame. That should be true on the Celsius scale as well. So what I'm getting at is, if there's a temperature change for some substance, if you were to double that temperature change on the Fahrenheit scale, the temperature change on the Celsius scale should also double. If you were to triple the delta T for the Celsius scale, you would also expect that the change in temperature for the Fahrenheit scale would also triple, etc. And this is just another way of saying that these two temperature changes are proportional. Regardless of which scale you're using, Fahrenheit or Celsius, the change in temperature on one scale should be proportional to the change in temperature on the other scale. Well, you're familiar with proportionality. This is the proportional symbol. You can, an equivalent statement would be to say that those two are equal with this so-called constant of proportionality out front. And oftentimes in the algebra books, they use a lowercase k as the constant of proportionality. But I'm not going to use that now, especially in these chapters, because the letter lowercase k has a very important role in thermodynamics. It's called the Boltzmann constant. We'll come back to that. So I'm just going to call the constant of proportionality capital A. Well, you remember what delta means. That's final minus initial. So I'm going to switch the notation just a little bit here. Instead of T sub C for temperature on the Celsius scale, I'll just use the letter C for the temperature. So C2 would be final temperature at time 2. C1 would be initial temperature at time 1. Both of those on the Celsius scale. Over here, we've got the initial and final temperatures excuse me, on the Fahrenheit scale. So this is just a statement that the change in temperature on the Celsius scale is proportional to the change in temperature on the Fahrenheit scale. Oh, I made another error here, so let me fix this. So I've retyped the equation up here, and now I'm going to change the notation slightly. Instead of talking about times 1 and 2, let's talk about times 0. This is some reference time, reference temperature, and then some arbitrary later time. So this is the Celsius temperature at some other time. This is the Celsius temperature at your reference time. And same thing for the Fahrenheit scale. It still says that the change in Celsius temperature is proportional to the change in Fahrenheit temperature. But now, let me distribute the A and move some stuff around. That's equivalent to this equation here at the bottom. This says that the Celsius temperature for any object or any substance is some constant times the Fahrenheit temperature plus, if you think about it, these are all just numbers, right? This is your reference temperature on the Celsius scale, reference on the Fahrenheit scale, and then the constant of proportionality. So all of this garbage is really just a single number. And now you may recognize that the equation we're looking at has the same form as y equals mx plus b. You've got a slope. You know, if you were to plot Celsius temperature versus Fahrenheit temperature, this would correspond to the slope, or it would be the slope. And then all this junk, you can just combine that and call it one thing. Let's call it b. That would be the intercept, the y-intercept, or in this case, the Celsius intercept. So we're looking at the equation of a line. Hopefully you already know that when you say two things are proportional, it means that when you graph them, you get a line. Okay, so I'm going to interpret that graphically. Here's the Celsius axis, here's the Fahrenheit axis, instead of y and x. And I've assumed a positive slope because obviously if the Fahrenheit temperature goes up, the Celsius temperature should go up as well, positive slope. And I've chosen two specific points that you're probably familiar with. You could call this the f-intercept. This is where the line intercepts the f-axis. And I've given it coordinates 32, 0, because I know that by design, the freezing point, the freezing temperature of water has these two temperatures on the two scales. So water freezes under normal atmospheric pressure. Water freezes at 32 degrees Fahrenheit, so that's the F coordinate. And by design, that would be 0 degrees Celsius. The Celsius scale is very sensible. The 0 degree point is taken as the temperature at which water freezes. And I should be specific, that's the temperature at which water freezes at sea level. Long Beach, basically. Some of you know if you took water up to the top of a mountain, it would boil and freeze at a different temperature because the pressure is different up there, the air pressure. Okay, the other one I took was the one I just mentioned, boiling. Hopefully you know that water boils at 100 degrees Celsius. That's why the Celsius scale is so convenient. Water is very familiar to us. Freezing and boiling, those are the two bookends of that 100 degree temperature range. It's also called the centigrade scale for that reason, 0 to 100, centi. Okay, 212 degrees is the temperature at which water boils on the Fahrenheit scale. So we've got 2 points there that we can use to figure out what all these constants are. So I rewrote this equation as Celsius temperature equals slope times Fahrenheit plus intercept. Well, there are 2 coefficients here, or 2 unknowns, that I'd like to solve for. So I'm going to use these data points to find those 2 unknowns. First, let's evaluate this equation at the freezing point of water. So 0 degrees Celsius is whatever that slope is times 32 degrees is freezing on the Fahrenheit scale plus your unknown intercept. And now let's evaluate this equation at the boiling point of water. That's where the Celsius temperature is 100. I plugged in 212 for the Fahrenheit temperature. And now we've got 2 equations in these 2 unknowns, M and B. Let's solve them. This should be simple. The top one says that B is negative 32M. And now I can take this expression for B and plug it into the second equation. How many M's do we have here on the right side? 212 minus 32, I believe that's 180. So I'll simplify. Boom. There's the slope. Solve for M. Well, 10 over 18 is the same as 5 over 9. Now we've got the slope in that line. And then, of course, since B is negative 32 times M, that's negative 32 times 5/9. Let's plug all that stuff back into the equation. So I've evaluated the slope. I've evaluated the intercept. Can't we factor out the 5/9? Okay, so you don't have to memorize this. It's not the most important thing really about this chapter, honestly. But if you want to convert from Fahrenheit to Celsius, plug in your Fahrenheit temperature and get Celsius out. First, you subtract 32. Let's do one in our heads. Room temperature. A lot of people prefer a temperature of 68 degrees in their room. So take 68, subtract 32. What would that be? 36. So the quantity in parentheses is 36. 36 divided by 9 is 4. 4 times 5 is 20. Okay. Room temperature on the Celsius scale is 20 degrees. That is easy to remember. Of course, you could invert this and solve for F in terms of C, and you would get this bottom equation now. So there are your 2 equations for converting from Fahrenheit to Celsius and vice versa. And I put this really heinous yellow background to help you remember this. Not the most important thing from the chapter, but it's worth knowing. But let's focus on the deltas. If you looked at the change in temperature on the 2 scales, you would find that again, this is your constant of proportionality. So I flipped it around. This is, whoops, this is the change in Fahrenheit temperature in terms of the change in Celsius temperature. 9/5, isn't that close to 10/5, which is 2? So here's a good number to remember. If you increase the temperature of like Earth's climate by 1 degree Celsius, that's roughly 2 degrees Fahrenheit. That's easy to remember. More precisely, or exactly, it would be 1.8. 9/5 is 1.8. Close enough to 2. Okay. How do you measure temperature? You don't even need a thermometer, right? Because we're all born with hands, most of us. And we've got temperature sensitive nerves in our fingertips. You can just touch something and you can tell how hot or cold it is in many instances. Now, that can be misleading. A lot of people, for instance, think that in the morning, bathroom tiles are colder than carpet. Because if you're standing barefoot on tiles, they sure feel cold, don't they? And the carpet does not. But a little thought should show you that the whole room should be at the same temperature, right? It's all in equilibrium. Why would the tile, what's keeping the tile colder than the carpet if they're right next to each other? The difference is the tile conducts heat from your foot more quickly. So heat is leaving your foot and going into the tile faster than it would into the carpet because the carpet's more of an insulator. It's really not to do with temperature. In any case, the most obvious or common way of measuring temperature or comparing the temperature of one thing to another is to use the expansion properties of a fluid. So we looked at this, you may recall, at the very beginning of the semester. We did that lab where we put a metal rod in a steam jacket and we measured how much its length increased in terms of the temperature difference. So remember, the simple statement is that the fractional change in length of something long, we're not talking about a cube here. A rod would be, you would apply this to something like a rod or a filament. The fractional change in length is proportional to the temperature change. So if you double the increase in temperature, you would expect twice the fractional change in length. What we didn't look at the time was volume expansion. For a fluid, which is not a metal rod, it actually makes more sense to talk about fractional change in volume because the fluid will expand in all directions. So instead of alpha, they go with beta. The fractional change in volume is still proportional to delta T. And you experience this every day, don't you? If you hear your home creak at night, you're hearing, I assume, wooden beams contracting as they cool off. And so everything's got to shift slightly to reach mechanical equilibrium. There's subtle effects, but we see them or hear them often. And there is a relation between beta and alpha, actually. You can look at that in your book. But the way this bulb thermometer works is usually this capillary is very thin, and you've got a quite a bit larger quantity of alcohol here. And that alcohol, when it expands, has really nowhere to go except for up the capillary. So you can calibrate the scale here, choose, plunge this thermometer into ice water, which we know is at freezing temperature. And then wherever the alcohol bottoms out, just mark that, call it 0 degrees. Then take your same thermometer, plunge it into boiling water, and wherever the alcohol ends up at that point, once it's reached equilibrium, mark that, call it 100, and then just chop the distance in between into 100 gradations. Okay. That's just a brief look at how to convert between the two. That's trivial, right? But it's a little more interesting to talk about what exactly is temperature. It's whether something's hot or cold. I suppose that's sufficient for a kid, but there's got to be something more fundamental behind it than that, because temperature exists with or without your perception. So is temperature merely what you read off the thermometer? I mean, again, that's just one way of probing temperature. Temperature affects things in other ways. We know that it makes other things expand besides just a column of alcohol in a bulb thermometer. So temperature isn't the behavior of the thermometer. That's just a symptom of what temperature is. And if you've never thought about this, challenge yourself. I mean, can you actually come up with something more fundamental? We know it has something to do with hot and cold. The temperature of a flame is much greater than the temperature of a glacier. And both of those are far lower, I expect, than the temperature of the surface of the sun. Or is that true? Because I'll point out that the light which comes from a flame, candle flame, is pretty similar in quality to sunlight. Here we're looking at the sun, from above the atmosphere. Or normally when you look at the sun or towards the sun, you're looking at it through the atmosphere of the Earth, and the light gets scattered and it's got different properties. But it's still kind of yellowish, right? Sunlight's kind of yellowish, and so is this light from candle flame. So we're going to see that the colors tell you a lot about temperature. Besides alcohol immersion thermometers, there's a whole bunch of other ways of measuring temperature that are probably more precise. You've got this bimetallic strip thermometer. Those are fun to read about, the way those work. They're very clever. And even more clever than that would be modern electrical thermometers. Maybe if you took 3B, you may have studied the fact that a resistor, here's some resistors, the resistance of the resistor in ohms changes depending on the temperature. So for instance, a light bulb filament, as the temperature of that filament goes up, its resistance also goes up, if I recall correctly. Yes, it does. But there are some materials for which the resistance actually drops as the temperature goes up. So if you've been, well, you don't have to do it yourself, of course. You could have a chart. If you're an engineer, you'd have a chart of a data somebody else had prepared. But if you knew exactly how the resistance changes with temperature, you could include that temperature sensitive resistor in a circuit and find some way of measuring the resistance whereby you could measure the temperature. So those thermometers are probably more accurate in a lot of ways than an alcohol thermometer. But these are all easily accessible physical properties. What about something, to use this, right? Wouldn't you have to immerse it in the thing whose temperature you're measuring, either your ear? Aren't there ear thermometers? Yeah, I think for little kids, or under your tongue. For the bimetallic strip, I'll be honest, I don't know what sort of device that would usually be used in, but usually there's some kind of contact involved in measuring temperature. What about the temperature of the surface of a star, though? If you've ever taken introductory astronomy or thought about it, astronomers talk all the time about the temperatures of stars. You can't go to a star and stick a thermometer in its ear because it would take a million years to get there at regular speed. So how do they actually know what the temperature is? None of the methods that require contact would work. So the only information we have from a star is the light coming from the star. That's the only thing fast enough to get here in any reasonable amount of time. So we have to look at the light, and light contains a wealth of information about the temperature of something. So this white curve, we're going to talk more about this towards the end of the semester, but this white curve shows you the intensity of light coming off the star as a function of wavelength. So you can see that for this particular star, most of the light is being emitted at a wavelength of around 8,000 angstroms. And an angstrom is a tenth of a nanometer. This star, which looks a little hotter, shall we say, it's actually peaking in the green part of the spectrum, around 6,000 angstroms. That would be 600 nanometers. So the distribution of light intensity as a function of wavelength depends on the temperature. The blue star is peaking actually outside of the visible spectrum. This is well beyond violet, so somewhere in the ultraviolet part of the spectrum is where the light is most intense. So by looking at the profile of that intensity versus lambda curve, you can infer something about the temperature of that object. In fact, it's a very precise way to measure temperature, and that is how some of these modern infrared thermometers work. I still don't have one of these, but they've got very economical. I think $20, $50, you can get a high quality infrared thermometer. I think you could even cook with it. If you want to know when, like, let's say you're making cheese from milk. Have you ever done that? It's a lot of fun. Very easy. You can get fresh mozzarella for just a couple bucks. That's the price of a gallon of milk. But you can measure the temperature of the surface of that milk just by, I believe there's a sensor here that is receiving the light, the invisible light coming off of the milk. And again, it's the profile, like what part of the infrared spectrum is most intense. By measuring that, the circuitry in here would determine the temperature. So I've got a more detailed picture here. Spectral energy density. Look at those units. Those are pretty gnarly. We'll talk about that more later in the semester. But here we're looking at various temperatures in kelvins. We haven't talked about the Kelvin scale yet, but it's very closely related to the Celsius scale. And this is showing you how much light comes out at various wavelengths. Now, for something that's not particularly hot, I mean, this is way hotter than anything in your room, most likely, but it's not as hot as the surface of the sun. So over 3,000 kelvins, the brightest light coming off that object would be in the visible part of the spectrum towards the red end. But you can see that as you make the object hotter and hotter, first of all, it puts out more light total. That's why each curve is taller than the previous curve, but the peak of those curves is moving towards shorter wavelengths. I can tell you right now that's called Wien's, W-I-E-N, Wien's displacement law. The hotter a solid object is, the shorter the so-called peak wavelength is. The greatest intensity will be emitted at shorter and shorter wavelengths as you make the object hotter and hotter. It doesn't mean it's not emitting light anymore at those other wavelengths. In fact, look at the green curve. It's emitting more light at all wavelengths than the object that's represented by the brown curve at the bottom, but it peaks at a shorter wavelength. Okay. So temperature is clearly more abstract or more general than just how hot something feels to the touch or the electrical or the resistive properties of a circuit component. It has something to do with light as well. Well, for our purposes, perhaps the most important definition of temperature we're going to see is that it tells us about the average kinetic energy of little particles of gas or fluid, even in a solid. Basically, the hotter something is, the faster the little particles zip around and bounce off each other, bounce off the walls of the container. That's it. That's how you should think about temperature in this chapter and subsequent chapters. The hotter a substance is, the more quickly its particles are flying around or jiggling. So we're going to see that the absolute temperature, that's the temperature on the Kelvin scale, that temperature is proportional to the average kinetic energy. I say average because this, if you really did have 3 atoms in a box, they're not all going to be bouncing around together at the exact same speed. At any moment in time, this one, for instance, might be going faster than the other 2. So you have to use the average. Now, even that definition is limited. That's just one manifestation of temperature. So if you want to go real deep and look for the most abstract, general possible definition you could think of, it's not this one. In fact, I should point out, hopefully we get to talk about this by the end of the semester. If you really did have 3 atoms in a small box, it's actually very naive from a modern perspective. It's very naive to think about those atoms as these little hard spheres, like little playpen balls bouncing around inside the box. As soon as you squeeze them into a rather small volume and they have any significant energy at all, they really do not behave like bouncy balls. They actually behave more like standing waves, which we looked at, I believe, in chapter 17. So this picture is rather naive. And if they're not balls bouncing around, then what does it even mean to talk about their kinetic energy? If they're a wave, what's the kinetic energy? What does that even mean? So this is not something you have to know. Don't worry about any of the symbols you see on this slide. I just thought some of you might be curious about the more abstract definition of temperature. I'll see if I can put it this way. Temperature tells you something about the way in which the possible, okay, let me try this again. I should have rehearsed this. If you've got a pot of water, maybe it's got 10 moles of particles. That's a whole lot of particles. Well, when you dump energy into those particles, they can distribute the energy in a whole bunch of different ways. Even if you only have 5 particles, 3 particles. If we go back here, if you dump some energy into this box by putting it over a flame, for instance, are you going to put all the energy into this one and none over here, or distribute it equally, or 60-40? There's a whole bunch of ways of distributing the energy. And that turns out to be related to temperature. When you put, when you dump more energy, you dump more energy into this box, uh, you open up more possibilities for the ways in which to share that energy. And the way in which that number of possibilities changes as you dump more energy in, that ratio, which is really derivative, that is basically temperature. So that probably doesn't make any sense to you. It's a very abstract definition of temperature. If you want to learn about that, you'd have to take a class in statistical mechanics. Really cool branch of physics. And any of you who plan on majoring physics will learn that stuff eventually. But I'll just point out here, T is for temperature. K is the Boltzmann constant, which we'll use a lot in subsequent chapters. E is for energy. And this W here basically is the number of ways of distributing energy amongst a bunch of different particles. And it's often an enormous number, unfathomably large number, which is why we take the log instead. So I'll come back with another video soon where we look at the ideal gas law and the notion of a constant volume gas thermometer. A few slides back, I showed you 3 different common mechanisms for measuring temperature. We have yet to talk about the most important one for these chapters, constant volume gas thermometer. And in the context of that discussion, we'll look at the ideal gas law. To be continued.